Swayam Prabha. Digital India. Educated India.
After noting that there is only one type of hexagonal lattice, let us move to the next type of lattice, which is the trigonal lattice. The typical unit cell used for the trigonal lattice is the parallelepiped, which is equilateral and equiangular. We just have one type of trigonal lattice, which is the primitive type. Another common name used for trigonal lattices is the name rhombohedral as well. So, whenever I am referring to a rhombohedral lattice, it is the same as the trigonal lattice. The characteristic of a trigonal lattice is the lattice parameter A is equal to B is equal to C, and all the angles are equal to each other but not equal to 90 degrees. So, all the angles are equal to each other but have a general value. The simplest way of understanding a trigonal lattice is by taking a cubic lattice like this. I hold a cubic lattice along the body diagonal, which is the one unknown direction, and then pull the cubic lattice. When I pull the cubic lattice, the distortion is such that all the angles are identical. The angles are not distorted. The lengths of the edges continue to be the same, which is A equal to B equal to C. All the included angles are identical, but they are not equal to 90 degrees. So, I can go from a cube to a unit cell which looks like the parallelepiped, which is equiangular and equilateral, by pulling along the body diagonal of a cube. This is, for instance, a typical unit cell shown on the left hand side, where you have the A, B and C vectors whose modulus are identical. The symmetry of all trigonal lattices is 3 bar 2 by m, and the important thing to note in these lattices is the position of the 3. It is located in the first position. Now, suppose I go back to my cubic crystals, or the cubic lattices to be more precise. In the cubic lattices, you see that there is also a 3 bar of the lattice, but it is located in the second position. Here, for the trigonal lattices which have a point group symmetry of 3 bar 2 by m, the 3 is located in the first position. So, this is an important thing to be noted, and this presence of 3 is the characteristic symmetry of all trigonal lattices. Unlike the cubic lattice, which has 4 such threefold axes. For instance, suppose I take a cubic lattice, and let me go and pick a model for you. So, this is my cubic lattice. Then this body diagonal is a threefold, this body diagonal is a threefold, and there are 4 such body diagonals. So, if I look along this, so there is one threefold like this body diagonal, this body diagonal, and the fourth body diagonal, which is also a threefold axis. But when once I distort it by pulling along this direction, which I have done so now, then I can clearly see there is just one threefold axis, that threefold axis being the axis along which I pulled the original cube. All the other threefold axes have been destroyed, and now I have only one threefold axis, which is along this body diagonal which I pulled. Now, let us now proceed to the next kind of lattice. One other point before we go to the next type of lattice is the point to note that sometimes people refer to a trigonal lattice by using a hexagonal unit cell. This is a possibility. At this point of time, we will not discuss this in detail, but sometimes when you see that people are using a hexagonal lattice or a hexagonal unit cell to refer to a trigonal lattice, actually it is just an alternate choice of the unit cell, but the lattice itself remains to be trigonal given the characteristic symmetry, which is the symmetry of the threefold in the first position, or a 3 bar as the lattices do have. If it happened to be actually a hexagonal lattice, it is very clear that it has to have a 6-fold symmetry and not a 3-fold symmetry. So, this is what I showed by the experiment, that I can go from a cube to a trigonal lattice by pulling along the body diagonal. Okay. The next lattice in the list is the monoclinic lattice, and the monoclinic lattices can be constructed or thought of by starting off with an orthorhombic lattice. So, suppose I have an orthorhombic lattice as shown in my model in my hand, okay, and which is nothing but a lattice in which the unit cell is chosen such that the A is not equal to B, is not equal to C, but all of them happen to be 90 degrees. But now suppose in addition I squash this in such a way that I distort it such that my A is not equal to B is not equal to C remains, but one of the angles is also destroyed from made different from 90 degrees, which is this included angle. As you can see from this figure, this angle is no longer 90 degree, which implies, or as in the figure, this angle beta is not 90 degrees. So, this is the angle beta which is not 90 degrees, but the other two angles are 90 degrees still. So, alpha and gamma continue to be 90 degrees and beta is not 90 degrees. So, the kind of unit cell you would use for this would be a parallelogramic prism. That means it is a prism whose, or to be more precise, it is a prism whose base is a parallelogram and it has been grown in the third direction, and such a prism will be the typical unit cell you would use for a monoclinic lattice. Now, there are many conventions of choosing the A and B's, but one convention is that we choose the A to be smaller than B to be smaller than C, and the conventions are helpful in communicating with other crystallographers. But if a different convention has been chosen to represent the same lattice, then that has to be explicitly stated so that there is no confusion as to which is the shortest or the next shortest or the longest lattice parameter among the three lattice parameters. The monoclinic lattice, there are two variants, the primitive and the C-centered. Apart from that, the body centered and the face centered monoclinic lattices do not exist. The symmetry of monoclinic lattices is 2 by m. That means the maximum symmetry it has got is only a two-fold and a mirror perpendicular to it, and the two-fold axis is typically positioned along the B axis, the two-fold axis, and the mirror will be what will be bisecting this cube along the vertical direction. So, the symmetry of monoclinic lattices is pretty low, but it still has a two-fold and a mirror symmetry which is characteristic of the monoclinic lattices. Now, the last in the list of lattices is the triclinic lattice. The triclinic lattice has no symmetry which is higher than a 1 bar. That means it is the lowest in terms of symmetry, and it is just the maximum symmetry possible is 1 bar. And if you look at the constraints on the lattice parameters, there is no constraint on any of the lattice parameters. A and B and C can take independent values, and also the three angles can be totally independent. So, this would be the case wherein the unit cell would be a general parallelepiped, okay. So, which is the most general parallelepiped, and we have already seen using a video that such a general parallelepiped can actually be a space filling solid. So, general parallelepiped, sometimes it is not obvious, can actually be a space filling solid, and we have seen a video to clarify this point. The only kind of lattice possible in this case is a primitive lattice, and as we shall see in later stages, that it is merely that whenever I have the other kind of triclinic lattices, since there is no symmetry, I can go on to choose other unit cells which would be a primitive triclinic lattice. So, to summarize what is there in this slide, the unit cell is a general parallelepiped wherein the alpha, beta and gamma are not constrained, and the A, B and C can take independent values and they are not equal to each other, and the only kind of lattice possible is the primitive lattice, and this is the lattice which has the least symmetry, and the symmetry of such lattices is 1 bar. That means there is just a center of inversion as far as this lattice goes. So, to summarize all the facts we have been considering so far regarding the shape of the unit cell and the typical unit cell used for the crystal and the lattice parameters, this is the list of all the things we have been considering so far. Now, we had asked ourselves an important question, that some of the lattices, for instance the orthorhombic lattice, had all possible entries, like you had a simple orthorhombic lattice, you had a face centered orthorhombic lattice, you had a C centered orthorhombic lattice, and then body centered orthorhombic lattice. But when you looked at some other example, for instance the case of the triclinic or the case of the trigonal, we saw that there is just one entry which is the primitive entry. There is no other So there are these extremes possible, and there are intermediate cases like the monoclinic where at least two kinds of lattices are possible. So this raises the obvious question, why are some of the lattices missing? Now we will take a few illustrations to understand the underlying principles which makes us understand the fact that why some of these lattices are missing. So let us review some of the points, that there are 7 crystal systems. Each of them, for instance, can have a primitive, body centered, face centered or seeds centering, which means there are 4 types in each of the 7 crystal systems. Then the potential number is 7 into 4, 28. But only we see that only half of them, 14, survive. That means only 14 of them are distinct, and the others is present somewhere in the list. The issue is that where do we put them? So all the 28 are present in some form or the other, but the question is that where do we put them in the list? Okay. And of course the basic rule has to remain that it has to be a lattice. That means it has to have identical surroundings. We have used the we will use the concept of choice of unit cell along with the classification to understand the existence of these 14 Bravai lattices. And we have already seen that the 2 important concepts when we try to understand crystallography is the concept of symmetry and size, which we shall invoke to understand the list of missing lattices. Okay. So for instance, let us pick up the first one. We see that a C-centered cubic lattice is missing. So like Mr. Patel asked a very interesting questions, the best way to find out if something is missing is actually put a C centering in a cubic lattice. That is what the good idea he had presented us with, and then find out why is it missing. And that is what precisely we have done here. We have taken a cubic lattice and we have introduced artificially 2 points, the top point and the bottom point, which are now the C centering lattice positions. Now what happens when you put in forcefully? We know clearly that the C centered lattice does not exist in the list. So we are forcefully adding these 2 points and trying to observe the effects of such an addition. The moment we introduce these 2 points in the top and the bottom, the characteristic symmetry of all cubic lattices, which is actually a 3-bar symmetry, and to just consider it a 3-bar symmetry as a subgroup, which is a 3 symmetry, we can see that that 3-bar axis or a 3-fold axis to be in a, if you want to consider just the proper rotation axis, has been destroyed by this introduction of a lattice point at the top and the bottom of the unit cell. In other words, I have taken my cube here as before. I have introduced one lattice point at the top and one lattice point at the bottom, and this operation destroys my 3-fold or a 3-bar axis which existed. And noting that a 3-fold is a proper rotation axis and 3 bar is an improper rotation axis, is being destroyed by this introduction of additional lattice points. And since a 3-fold is a characteristic symmetry of these lattices, such a lattice cannot exist very clearly based on the rules of symmetry. Now additionally we will notice that if I do such an operation of introducing a point at the top and a point at the bottom, this 4-fold axis remains as before. This 4-fold axis and these 4-fold axis have been destroyed. Note however that when we are talking about cubic crystals, which we will consider in detail very soon, and this is just a prelude to the understanding of cubic crystals which are based on cubic lattices. Cubic lattices need to have this 3-bar or a 3-fold rotational axis. Cubic crystals need to have again this 3-fold rotational axis, but cubic lattices always have these 3-4-fold, but cubic crystals need not have any 4-fold rotation axis. Therefore cubic crystals, when I am talking about cubic lattices, I need to worry about this 4-fold also. Of course if 3-fold is destroyed, it is no longer a cubic lattice, but additionally even the 4-fold rotation axis, 3 of them, 3 are mutually perpendicular 4-fold axes are present in a cubic lattice, and if that symmetry has been destroyed, then obviously it is not a cubic lattice. Now the question is that where do we place? That means what do we choose? The question is we are asking is that what is the preferred lattice we choose for this, or the preferred unit cell which will go on to describe the lattice. The one we choose is shown in the figure at the bottom, and that is a simple tetragonal cell. So in other words, there is no possibility of having a cubic F, because a cubic F needs to have a 3-bar or a 3-fold, but you can make a choice of a unit cell which is, for instance, the simple tetragonal cell, which will put this kind of a C-centered cubic in the simple tetragonal or the tetragonal class. I have here a model with me which will explain you how this has been done. So, this is my model of the same thing. So, you can see here that I have introduced these two centering points at the top and the bottom, and what I have done is made an alternate choice of the unit cell, and now this alternate unit cell, which is marked in yellow, is a simple tetragonal cell. It as far as the cell goes, this is a lower symmetry cell than the cubic cell, which is blue, but it is smaller in size, as obvious from this figure. So, it is a smaller cell, it is a primitive cell, that means that there is only one lattice point per cell. So, looking at the figure once more, so you can see from this angle also that I have this blue unit cell, which is two unit cells of the cubic lattice. I introduce a lattice point at the top and the bottom to forcefully make something known as a C-centered cubic, which we consider to be banned because of the fact that there is a violation of symmetry of the cubic lattices, but then we can go ahead and make an alternate unit cell, which is the yellow unit cell, which is nothing but a simple tetragonal cell. Let us consider another example. We have seen, like in the cubic case, the C-centered lattice is missing. In the tetragonal case, the F centering is missing. So, let us see why this F centered tetragonal is missing. And like before, we see here that there is an orange unit cell, which is a combination of two unit cells. I now put in my additional lattice points on the tetragonal unit cell. For instance, I put these orange points, and there is one marked in green, but please note all points are identical, they are lattice points. So, lattice points cannot have color or any other kind of attribute to it. So, it is just shown in different color, so that for you to understand that it is that point which is exactly between the two unit cells. So, I have all these lattice points, some of them are at the face centers and some of them are the corners of the way the unit cell has been represented. Now, for such a face centered tetragonal lattice, what I can do, I can go ahead and make an alternate choice of a unit cell, which like before happens to be this blue outline, and you can see that this blue outline has one point in the center at the body centered. That means that I can make an alternate choice of an unit cell for the face centered tetragonal case, and therefore that alternate choice is a body centered tetragonal lattice. Now, should I use a face centered tetragonal or a body centered tetragonal? The choice is obvious, because face centered tetragonal has 4 lattice points per cell, the body centered tetragonal has only 2 lattice points per cell. I go ahead and make the smaller unit cell, which is the blue unit cell, as my preferred choice, and therefore instead of having a face centered lattice here, what we choose here is a body centered tetragonal lattice. So, it is an alternate description of the same lattice. The lattice has not been what you call thrown away in any sense. Its symmetries exist as it were, but only thing, where do I place it in this scheme of things is the question I am asking, and in the scheme of things I am not putting it under the basket called face centered tetragonal, I put it under the basket called the body centered tetragonal lattice. Okay. Now, let us consider another example to understand the mystery of these missing lattices, and here we see that there is no possibility of having, or at least there is no in the listing, there is no C-centered tetragonal lattice. Okay. And what I can do in the case of C-centered tetragonal lattice is go ahead and make an alternate choice like shown in this case. That means I enforce additional lattice points in C-centering, the top and the bottom, and I get a simple tetragonal lattice. Now, since the symmetry of these two lattices is exactly identical, the only consideration which comes into play in this choice is the size. Like in the previous case, I have no worry of transferring something from here to here, because the symmetry of both face centered and body centered tetragonal lattices are identical, both are tetragonal lattices. Similarly, the issue which came into play here is the size, and you can see that both these tetragonal unit cell have 4-fold symmetry axis. In the previous case, the 4-fold axis would have been vertically here, or in this case also there is a 4-fold rotation axis, and we know that tetragonal lattices have one and only one 4-fold rotation axis. So, let us maybe just go back to the slide where we considered the tetragonal lattice. So, this is my tetragonal lattice, and the characteristic symmetry of tetragonal lattices is this 4 by m symmetry, and if you want to write down the full symmetry of all possible tetragonal lattices, it is 4 by m, 2 by m, 2 by m symmetry. And when you go down to this case of the face and C-centered tetragonal lattice or its alternate choice as the primitive tetragonal lattice, both of them have a 4 by m, 2 by m, 2 by m kind of symmetry. Therefore, instead of placing something under the C-centered tetragonal class, I just transfer it to the primitive tetragonal class, and therefore it has been repositioned. So, we make an alternate choice. So, this is what we choose. Now, some of the other choices we will try to enforce and see what happens. For instance, for the missing case, for instance, there is one missing lattice, the body centered hexagonal lattice. We had mentioned there is just one kind of hexagonal lattice possible, which is the simple hexagonal lattice, and we had further even asked the question that when we typically we have seen in textbooks that there is something known as hexagonal close packed crystal, wherein there are additional atoms located somewhere within the unit cell. We will answer that question a little later, that where this additional atom comes from, but before that we consider the issue that why there is no body centered hexagonal lattice possible. So, this was the typical hexagonal lattice which had this characteristic 6-fold symmetry which we had noticed. And now what we try to do, and of course this was the original hexagonal lattice wherein which is shown in projection, that means I am looking down the C axis from the top axis and I am seeing such a projection along the basal layer. So, along this point, for instance lattice point, there will be one point here and one point here which will be projected down onto a single point on the projection. Similarly, each one of the points here is nothing but a projection of a top and a bottom point onto a single layer. Okay. Now, we had also considered that this is my choice of the unit cell which is shown in the blue outline or in the projection as a shaded blue area. Now, what I try to do, suppose I try to make a forcefully a body centered tetragonal, a body centered hexagonal lattice. That means in addition to the original lattice points which are located at the vertices of these rhombic prism, I introduce additional lattice points. So, let me try to do this in a model which I have got here. So, now assume that this is my simple hexagonal lattice. So, as before I will have to assume that these are not actually any entities, but actually they are points. So, in this point suppose I want to introduce a body centered hexagonal, that means I put additional lattice points at the center of this body. Let me choose a smaller point, for instance let me take a smaller sphere which will be make it clearer. So, I can put one point, one body centering point here, I can put one body centering point here and so forth, and I can construct a body centered lattice of the hexagonal class. So, once I have done the job, I can view the same thing along the 3-dimensional perspective or the projection. So, when I put these additional points here, for instance I put one here, I put one here, I put one here, and note that these points are not located on the top face or bottom face, they are located at the distance such that z is equal to half. Okay. At z equal to half they are located. So, this point is actually halfway from the top and the bottom of the unit cell. If I want to look at these points, then these points are located midway, they are located in the mid plane at the body center right here. Okay. Now, if I do such an operation, it is very clear that the 6-fold symmetry will be destroyed. Again, there is a point to be noted here that 6-fold symmetry is a characteristic of all hexagonal lattices, but is not a requirement. What I mean here is a pure 6-fold and not any of the variants like a screw 6 axis, but a pure 6-fold is not a requirement for hexagonal or crystals. You can make crystals out of hexagonal lattices which may not have this pure 6-fold rotation axis, but hexagonal crystals always have this kind of a characteristic symmetry, and once I have destroyed this characteristic symmetry by putting additional points here, then such a lattice is not allowed under the hexagonal class. Similarly, let us consider another missing kind of a lattice. Now, in this case it is the missing face centered hexagonal lattice. So, as usual I have this original hexagonal lattice which is the primitive hexagonal lattice which has got a characteristic cis-fold axis, and we already saw this projection wherein I had projected 2 layers these two layers onto a single layer wherein I had marked the conventional unit cell. Now what I try to do, I try to additionally add face centering points. That means I take each unit cell and on the unit cell I try to put additional face centering lattice points. So let me try to do this in the model first and then on the computer. So I have this model here, and what I try to do, I take a additional lattice point, I put it at this face center, I put it at this face center. So now you have to focus on the red unit cell, the unit cell which is the red unit cell, right. So I put it at this face center, 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 and all these four face centered are located at the distance c is equal to half. Additionally, there is this top face center where I put one point right here and I put one at the bottom face center. So I have got four vertical faces whose face centers I put this additional lattice point, and I have one face center at the top and one face center at the bottom wherein I locate my additional lattice points. So I add 4 plus 2, 6 additional lattice points on this original primitive hexagonal lattice. So whenever I do so, what happens? I see that, so this is my unit cell, and for clarity I have just marked all these face centering points on a single unit cell, not on all the unit cells which are contained within this hexagon. So I show that there is one at the top, one at the bottom, and just for clarity these 2 points have been shown in orange, while all the points located at c equal to half are shown in green, and the vertices of the original hexagonal lattice have been shown in blue. So this is just merely for clarity, and you can see that if such a operation I do, then my 6-fold axis will be destroyed. Okay. And if I had original 6-fold axis, then I need to have, if I have a lattice point here, there should be one here and so forth, but they are missing. Clearly you can see that at this top and bottom face I have one here, but the next point is here and there is none here. That means if I had original 6-fold, then this point will be taken by the 6-fold to here, it will be taken here, 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 and I would have a complete 6 identity points which will be left by the 6-fold operation. Since these 2 points do not exist, therefore the 6-fold axis has been destroyed, and therefore I cannot have a face centered hexagonal lattice. So we have already considered a few cases so far. We have seen that C centered cubic is not possible based on the argument of symmetry. We have seen that the face centered tetragonal is placed under the body centered tetragonal, and this was purely because of the choice of the size factor. Then the C centered tetragonal was placed under the primitive tetragonal, and this was again a size based argument. When it came down to the 2 hexagonal ones we considered so far, it was a symmetry based argument that we said that such kind of hexagonal lattices are not possible. Let us consider the last in the hexagonal list which is missing, which is the C centering, which is not possible, and this is of course a very simple choice. Herein I take this my original hexagonal lattice shown in perspective and projection, and to introduce additional 2 lattice points which are shown in orange color for differentiation. So now I introduced C centering to my original hexagonal lattice. Now in projection you can see that such a centering would lead to centering in all the unit cells. So this is my unit cell, and this unit cell will be translated to this unit cell and correspondingly to all the unit cells in projection. So let me again show this using the model. So this is a simpler case than the others before, because we are just introducing 2 additional points, and these 2 additional points are one at the top because this is C centering and one at the bottom. So I have introduced my C centering, and when I do such a C centering, I clearly see that such a unit cell, such a kind of a lattice is not possible, because now as before if I do the C centering, then I will have one point here, one point here, one point here, one point here, which are located in the plane, basal plane, and the plane which is shifted by distance c. And if I had to have 6-fold symmetry, then I need these additional points as well, right here, right here. And since I need one here, I need one there, and I will need one there, one there. Since these ones marked in red are not possible, therefore the 6-fold symmetry will be destroyed when I take a make a C centering. And now of course as before we are making a forceful C centering, which is the idea suggested by Mr. Patel, that we are doing a forceful C centering, and this forceful C-centering will destroy my hexagonal symmetry, which is characteristic of all hexagonal lattice, the six-fold, and therefore I will not have a C-centered tetragonal or C-centered hexagonal lattice. We have seen so far that, for instance, what is the choices we make. Let us see some cases of choices which we do not make. Okay. For instance, let us see the example as shown here. I have a cubic lattice, and in this case it is actually a face centered cubic lattice. That means that there are additional lattice points on all face centers. Now, can I go ahead and make an alternate choice of a unit cell? For instance, this unit cell shown in blue outline. Clearly, the unit cell shown in blue outline is a smaller unit cell. In this case, it happens to be a body centered tetragonal lattice, because there is one at the center of the body of this tetragonal, okay, unit cell. But can I make such a choice? Does it sound logical, and would I further take it and make it a conventional unit cell to describe these kind of lattices? The answer is no, we do not make such a choice, and the reason is that the face centered unit cell has an higher symmetry. In other words, the lattice has, you know, 4 3-fold axes, which can be generated starting with 2 3-fold axes, and therefore I would like to make a unit cell choice also, or a description of the unit lattice in terms of unit cell which has that kind of a symmetry, and therefore I will not make a choice of a unit cell which is the one shown here, which is a tetragonal unit cell which has just 1 4-fold axis and no 3-fold axis. The face centered lattice had 4 3-fold axes and 3 4-fold axes, which are all missing, or some of that is missing in the tetragonal unit cell, and therefore I do not make a choice of the smaller tetragonal unit cell. That means, even though it is a smaller unit cell, the unit cell itself is a not the preferred one. And another point again to be noted, which we have been emphasizing quite a bit, that my mere choice of the unit cell is not going to alter the lattice. The lattice will always remain a face centered cubic lattice, because it has got the symmetry of a cubic lattice, and it can be described by unit cell which has that kind of a centering along all the faces. However, for some reason, if you want to make a choice which is given by the blue outline and call it a body centered tetragonal unit cell, yes, you are fine to do so, but the lattice itself will always remain a face centered cubic lattice, because that lattice, the description of that lattice is characterized by the 4 by m 3 bar 2 by m symmetry, which will not be destroyed by your mere choice of the unit cell. However, the conventional unit cell is the one which is chosen in orange. So, when we consider lattices, what we are merely doing at times is actually transferring some of the lattices from one place to the other, and I thank Professor Rajesh Prasad for this slide courtesy. And you can see that I can take, for instance, the C centered cubic and I place it under the primitive tetragonal. The face centered I do not move to the body centered tetragonal. The face centered cubic is not moved there. I move the face centered tetragonal to the body centered tetragonal, and I make such kind of rearrangements, but in the end I land up with only 14 distinct lattices, which are the 14 Brabhai lattices, okay. And that is all the possibility we have got. It helps us in many ways in understanding a lot of the concepts we have seen before, including the concept of a sublattice, okay. Now, the property of the lattice we are talking about is that any point in the lattice you sit, all the space that around you would look identical. It does not matter where you sit, which lattice point you choose to sit on, entire space will look exactly identical given the array of points. For instance, if you take a one dimensional lattice, we had already seen that if you sit here, there is one point to the left at a distance a, and there is one point to the right at a distance a. Now, instead of choosing a lattice point, I could choose a point, for instance, which is at a distance x to the left of a lattice point. If I do so, then all the points which are at a distance x to the left of the existing lattice would in some sense form another lattice, which will again be identical. In other words, if I sit at this point here, just at a distance x to the left of the lattice point, then all the points which are at a distance x to the left of the lattice point would form an array of points from where space would look identical. So, this is another way of looking at the same point. So, we can chart out a set of equivalent points in space which may or may not coincide with the original lattice. And for instance, in the example, the one dimensional example I have shown below, all the points marked with a circle or filled circle form a lattice, and all the x's marked in x are also forming an equivalent lattice. So, this is an important point, and let us consider 2-dimensional and 3-dimensional analogues of this same concept. That means that suppose I had a lattice, I generated a point by moving it by distance x, and I sit in this point x, then all these other x's which have been generated by the same lattice translation vector or a translation vector would form a lattice which is exactly identical to the original lattice. So, suppose I sit in the blue sphere or this blue sphere or this blue circle, sorry, these are all circles in 2 dimensions. So, if I sit here, it does not matter to me, and space will look exactly identical. Similarly, if I sit here or sit here or sit here, space would look identical to me. And how will the space look? If I sit here, then to this vector I will find one blue point, to this vector I will find another blue point, to this vector I will find the third blue point and fourth blue point, like this. Similarly, I sit here, exactly the same kind of an environment will be seen by me. So, the x's themselves are a 2-dimensional lattice which is exactly equivalent to the original 2-dimensional lattice. Carrying forward this analogy to 3 dimensions, I can do the same operation in 3 dimensions. That means I can start from any origin in the 3-dimensional lattice. For instance, this is a cubic lattice, and I can define a vector, right. Now, this vector will take me to a point x. Suppose I start with this point, it will take me to another point x. If I start here, it will take me to another point x, and so forth. Now, the important point to be noted is that all these x's themselves are contributing to the lattice which has been shown by this alternate unit cell, which is the dotted unit cell. In other words, if I sit here, then or sit here does not make a difference. Similarly, if I sit at this point or this point, my environment will be identical. Noting that again once more, that the lattice I am considering is not made up of these x's, the lattice is originally consisting of these points, the vertices of the blue unit cell. So, now if I sit here, then I would find a lattice point at a distance a, for instance a along this direction, b along this direction, c along this direction. Similarly, if I sit here, I would find exactly an equivalent point along a along this direction, b along this direction, c along this direction. So, this concept of an identical surrounding is very, very important, because when we try to make alloys and try to locate interstitial voids along which other kind of atoms or other kind of species would sit, this identical surrounding is a very, very important concept. So, just peeking ahead, we will come to this concept a little later in the course. If, for instance, given a crystal, for instance an FCC lattice decorated with an atomic motif, and now I am talking about a crystal which is commonly called a cubic close packed crystal. The edge center, if for instance is a position of the octahedral void, then the set of octahedral void positions will also form an FCC lattice. So, this is an important property. Just to repeat the sentence, if for a given crystal, for instance a cubic close packed crystal, the edge center is a position of an octahedral void, then the set of octahedral voids positions will also form an FCC lattice. So, this is something to be remembered.
Suppose if a crystal is there and there is any vacancy in dislocation. So, I think this symmetry can be some disturbed.
Okay.
Dislocation will be there some.
Okay. So, let me repeat Mr. Patel's question, that if there are dislocations or vacancies in the crystal, then what happens? This is a very advanced question at this stage, because so far we are only considering ideal perfect crystals, but nevertheless is a very important question which we will take up in detail. To answer some part of his question for now, let us consider the case of the vacancy, for instance, right. Suppose now we are considering the concept of a sublattice, right. So, we could construct a sublattice which is completely vacant. That means that I could make a sublattice out of vacancies. So, I would make a sublattice, I put just vacancies in that sublattice. For instance, in the cubic crystal. Of course, if I have to be a little careful in doing the operation, otherwise the cubic symmetry may be destroyed. Suppose I am assuming that the cubic symmetry can be destroyed, and I start putting vacancies in every second point. I will go along the x direction, I don't put a vacancy here, put a vacancy here, then don't put a vacancy here, put a vacancy here. So now I start putting vacancies in every alternate set of points. I can do that just for the sake. Now we will see that all these kind of vacancies can form a sublattice, but now the sublattice is not occupied by an atomic species but by a vacancy. We will return to these concepts in a little more detail when we actually talk about defects in materials, and for now we will leave this advanced topic and try to understand some of the other topics which are very, very important. Now the next few slides are again some sort of a peek ahead, which we will explain very soon, but you should remember some of the things mentioned in these slides are very important and often not clearly emphasized in some of the elementary textbooks. So the important thing is that crystals and crystal systems are defined based on symmetry and not on the geometry of the unit cell. So whenever I am talking about a cubic crystal, I do not mean A equal to B equal to C and alpha is equal to beta is equal to gamma. What I mean is the existence of a or two threefold axes, which actually mean these two threefold axes will automatically generate the four threefold axes, and therefore a cubic crystal will always have four threefold axes. Now the reverse is however true. If I already have a cubic crystal, then I will obviously make a choice of an unit cell axis, which is A equal to B equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees. So now we can ask ourselves a few questions which are very, very important. If lattices are based just on translation, then how come other symmetries, especially rotational symmetries, come into the picture while choosing the crystal system and the unit cell for the lattice? So some part of this question we had already asked, and in that sense it is just a revision of that question. The question we are asking is that if lattices are based just on translation, then how come these other symmetries, especially rotational symmetries, come into the picture while talking about the concept of a crystal system or the choice of the unit cell? For example, why do we say that end-centered cubic lattice does not exist? Isn't it sufficient that A equal to B equal to C and alpha beta gamma equal to 90 degree to call something cubic? In other words, why do we put the end-centered cubic into the simple tetragonal? We had answered this question just some time back, and the answer was that, and to generalize the answer, the issue comes because we want to put the 14 Bravais lattices into 7 boxes, the 7 crystal systems. These 7 crystal systems have 7 distinct symmetries, okay, and further assign unit cells to them. So not only we want to put these 14 Bravais lattices into 7 boxes, but we want to assign unit cells to them as well. The crystal systems are defined based on symmetries, and these are rotational, mirror inversion, etc., which we had considered at the beginning of this course, which go on to form the point group and not on the geometry of the unit cell. On the other hand, the choice of the unit cell is based on symmetry and size, and also some amount of convention wherever symmetry and size fails to resolve the issue. In practice, the choice of the unit cell is left to us. We have seen that is something which is under our control, but what we call a crystal is not. So this point has to be clearly understood, that a crystal is based on symmetry, and therefore it is not left to us to call what that a given crystal is. It will automatically choose its crystal system. So once more we try to revise this important concept. As I pointed out, this important concept is often not clearly explained in some very elementary material science textbooks, so we need to look at it a little carefully. When we say use the word end-centered cubic, end-centered is a type of lattice which is based on translation. Cubic is a type of crystal based on other symmetries. Cubic word also refers to the shape of the unit cell, which is based on lattice parameters. So here the confusion, it's the reason for confusion, because now we have 3 concepts, one based on translation, one based on symmetries, one based on choice of lattice parameters, all coming together in a single phrase, end-centered cubic. Okay. And to note, cubic word has been used in 2 contexts, one to refer to a crystal, one to the choice of the unit cell, right. So this is and if this kind of a confusion is not enough, there is further confusion coming up, because cubic crystals can have symmetry which is lower than that of the cubic lattice. So far we have been talking about the cubic lattice, and just to reiterate, because this is such an important concept, let me go down to the board and write down the symmetry of the cubic lattices, which we did before. So this is the symmetry of all cubic lattices, but cubic crystals can have symmetry which is lower than this. So for instance, cubic lattices always have fourfold symmetry, but cubic crystal may or may not have this kind of a fourfold axis. So as you can see, because of terminology, of coming together of a confluence of concepts, translation based, symmetry based, and certain things which are unit cell convention based concepts, there is scope for considerable confusion. So it is now up to us to actually clarify the situation, and we will try to make things crystal clear by quite a few examples which are coming up very soon, and we will also try to answer some of the questions which we have raised in the previous slide and the next slide. So we will try to make as far as possible the concepts crystal clear. I was mentioning about the word cubic. Just to summarize once more, the word cubic refers to three things here. It refers to a type of lattice, it refers to a type of crystal, it also can refer to the shape of an unit cell. So please remember once more that the word cubic has been used in more than one context, and this is the reason for considerable confusion, or the reason why often when we write or we read textbooks, it can lead to some kind of a misunderstanding related to this concept. So the word cubic can be referring to the kind of lattice we are talking about, it could be referring to a kind of crystal which is a symmetry based concept, or we could just merely be referring to the kind of unit cell we are talking about. And hence we need to be little careful when we are dealing with all these words and these phraseology in crystallography, and we will take up examples to show that crystals based on a lattice can have lower symmetry than the lattice itself. In other words, the motif we put on the lattice can lead to a lowering of the symmetry, and we will take up this as the next set of examples, which will, I am sure, make the concept clear beyond doubt. So let us try to make some crystals in 1 dimension, 2 dimension, and 3 dimension to understand some important concepts, especially related to the lowering of symmetry on the formation of a crystal. And we shall use our familiar language of crystallography to understand these concepts. Let us start with 1 dimension, and this we have already considered before this example, wherein we took a motif which is in the form of a line segment, and we decorated a 1-dimensional lattice to form a crystal. Now we just stated that crystals can have lower symmetry than the lattice from which we start off with. So let us look at the symmetry of the lattice. Now if I look at a 1-dimensional lattice, we can clearly see that the 1-dimensional lattice has mirrors, vertical mirrors in the position of the lattice point. So you can see that this is the lattice point, the next lattice point is here, and the next lattice point is here, and these are seats of vertical mirrors. That means that this mirror will take my lattice point from here to here. So therefore all vertical mirrors are located at lattice points. Additionally, there are mirrors which are located exactly between 2 lattice points. For instance, I consider this mirror which I call MV2, mirror vertical 2, while I call the first mirror which I considered as the MV1, which means the vertical mirror 1. So the second mirror, which is completely independent or of the first mirror set of mirrors, again please remember that all such 1-dimensional lattices obviously have a translational symmetry. That means that if I may put a mirror in my lattice point here, the translation symmetry will take that mirror to the next position, to the next position, to the next position, and to the next position, and so forth. In other words, by just putting one mirror plane in a lattice point, I will actually obtain an infinite set of mirrors at all lattice points, which is just nothing but stating the important property of symmetry, that symmetry operators operate on entire space and everything which is included in it. In this case, what is included in the space is this mirror plane. So the mirror plane is taken from lattice point to lattice point. The second mirror is located between the lattice points. So let me take this vertical mirror. For instance, it takes this lattice point from here to here. Therefore, since these two are lattice points here, therefore This is a mirror plane. Now again translation will take this mirror from here to here and to here, which is nothing but all are but a set of pre-existing mirror symmetries of this lattice. Additionally, because we will see soon that we will also consider, we have done this before. For instance, we have tried to put 2-dimensional motifs on a 1-dimensional lattice, right? And if you do so, then we need to consider an additional symmetry of this lattice, which is a horizontal mirror. For instance, this lattice also has got a horizontal mirror, which I call as an MH. So the combined symmetry, or putting together all the symmetries of this 1-dimensional lattice, it has a translation, which is the generator of this lattice. There is a horizontal mirror, there is a vertical mirror 1, which is located at the lattice points, and vertical mirror 2, which is again an equivalent set but displaced by distance half the lattice parameter. So to write it in a very shorthand form, I will call it as an MMM symmetry, which is a symmetry of all 1-dimensional lattices. So this 1-dimensional lattice has definitely, every 1-dimensional lattice has to have this MMM symmetry. Now you can also consider certain redundant symmetry operators also, for instance, which arise purely because of the existence of these mirrors, that for instance these points can also be centers of inversion. So but this is a redundant symmetry operator because this comes in addition, or the lattice itself does not need this kind of a symmetry operator to be generated. So you can describe this kind of a lattice either in terms of the mirror planes or in terms of this inversion symmetry. Additionally, of course, you could also consider two-fold axes, which are also redundant symmetry operators, and the reason that the inversion can be replaced with two-fold is because in 1 dimension there are no left-handed or right-handed objects which can be distinguished between a two-fold, which can distinguish you from a two-fold from a inversion operator. So since there are no left-handed or right-handed objects in 1 dimension, we can use either a inversion operator or a rotation operator to generate this lattice. Now let us read out some salient features of this kind of a analysis. It is true that some basic set of symmetry operators can generate the structure. It is also true that some more symmetry operators can be identified which are not envisaged in the basic set, and we call them redundant. Of course, what we call set 1 or set 2 or what we call the basic or redundant is left to us, but essentially the structure has all these kind of symmetry operators. And let us try to decorate this lattice with some kind of a motif and see what happens to the crystal we are generating. Now each one of these examples in this slide and the coming slides are crystals which have been generated using the lattice. Of course, we will not focus on every one of these examples, but I will take a few of these which are shown in the slides to illustrate the important point. Now suppose I put a motif, and now the motif is a double-ended arrow, an arrow which extends from top to bottom. Then I see, of course, this is my unit cell of the lattice which is extending from here to here, and what happens to the symmetry? I clearly see the symmetry of the lattice has been conserved, it has been maintained. There is no loss in symmetry when I put my motif. In other words, what is the symmetry of the crystal which I have obtained? The symmetry of the crystal is MMM. The horizontal mirror still remains because the motif has a top and bottom ends to its arrow. The vertical mirror located at the lattice point remains. The vertical mirror between the lattice point also remains. So I could write such a crystal having a symmetry as T, MH, MV1, MV2, or in a shorthand notation as MMM symmetry. So I could have motifs which conserve the symmetry of the lattice, and this is what precisely has been done in this crystal. Now I could choose motifs with lower symmetry. Now I am talking about symmetry of the motif and not symmetry of the crystal or lattice so far. So I can choose a motif which has lower symmetry. Now for instance, the motif which I have chosen for the second example is our familiar arrow mark, which is pointing upward. It is not the double-ended arrow as we saw before, it is a single-headed arrow. Now what happens if I put such an arrow at each lattice point? I would get a crystal. So this is my crystal number 2 in the list. Let us analyze the symmetry of this crystal. Symmetry of this crystal is that you can clearly see the horizontal mirror has been destroyed. Vertical mirror 1 remains, vertical mirror 2 remains, the translational symmetry still remains, Therefore, in shorthand I can write the symmetry of this lattice or this crystal, to be more precise, the crystal to be T MV1 MV2, or in shorthand notation as MM symmetry. The MH, the horizontal mirror, has been destroyed and the crystal has only MM symmetry. That means that the crystal can have lower symmetry than the lattice I started off with. This is an important point to be noted, and so far there is just a slight reduction in the symmetry of the crystal with respect to the lattice, which is a loss of a single mirror. We will go ahead and consider other examples where the loss in symmetry could be more, and that is what we consider next. Just to reiterate the important salient feature of this slide, this crystal has an MM symmetry, MV1 MV2 symmetry, or to be extensive T MV1 MV2, while the lattice itself had a T MH MV1 MV2 kind of a symmetry. I will skip this slide, which involves certain symmetry operators like the glide reflection operator or the inversion operator, but these also serve to illustrate the same point. Since we are focusing on the important point regarding the loss of the symmetry, let me take another example of a motif which is listed as number 5. Here what I am doing, I am putting a motif which is in the form of a double flag, a flag on the top and the flag on the motif. So this entire object is my motif, and I put it at each lattice point. In this case what happens? What happens is that all the vertical mirrors are destroyed. The vertical mirrors in lattice positions and the vertical mirrors in the between the lattice positions, because if I put a lattice mirror in the lattice position, for instance, let me pick I draw a mirror here, for instance, between the lattice points, then this object will have to be reflected on the other side, and it will have a shape which is like this, which is obviously not present, right. So this object which will be reflected will actually be an arrow having a double-ended arrow like this, which is not the case, and this is the object which is there. Therefore, you can clearly see that both the vertical mirrors MV1 and MV2 have been destroyed by putting a motif on the lattice points. In other words, the crystal I have generated here has a lower symmetry than the original lattice, and the only surviving symmetry is the horizontal mirror, which is MH. The translation symmetry remains, so I can write the symmetry of the crystal I have generated, number 5 crystal, as TMH. So this crystal, as you can see, has a lower symmetry than the lattice I used to generate. Let us take an extreme example, which is number 7 in the list, wherein I put a motif which is in the form of a single flag at each lattice point. What happens to the symmetry of this crystal, or what is the symmetry of this crystal with respect to the lattice from which I started? Such a crystal has only translational symmetry. So there is the horizontal mirror has been destroyed. So if I draw this horizontal mirror, this has been destroyed. The vertical mirrors which existed between the lattice points have been destroyed. The vertical mirrors which existed at lattice points have been destroyed, and therefore there is only one kind of a symmetry which remains, the translational symmetry. I have lost all my mirrors. Now, two important points to note. First thing, this is still a crystal. Why is it a crystal? Because it has got translational symmetry, and as we shall see by later examples, if even this translational symmetry is lost, then we can no longer call such a substance or such a crystal, such an entity or such a structure as a crystal. Number 2, the loss in symmetry could be so extreme that even if the original lattice had quite a bit of symmetry, like in this case MMM symmetry, if the loss could be so severe that you are just left with translational symmetry. That means the motif could be so irregular, or as in this case it happens to be the shape of a flag, it does not conserve any of the symmetries of the original lattice, and therefore I have lost all my mirror planes, but as long as the translational symmetry remains, I can call it a crystal. So this is something which I need to note, and this is the important point, and I will take up more examples in 2 dimensions to exemplify some of these points and introduce certain other concepts which cannot be introduced in 1 dimension.